Hello, my name is Nick Brandreth, and here's a presentation on early motion picture filmmaking. To make a light-sensitive material, we need two things. The first part is silver nitrate, and silver nitrate is pure silver dissolved in nitric acid. So here's a pure silver coin, so 0.999 silver. The coin is placed into a vessel that can withstand some heat. We add the nitric acid, and this will eventually bubble, pop, and fizz, and the coin will be completely dissolved, and after several applications will be left behind with this fine powder. Okay. The other part that we need is a halide, and the halide is a halogen, which is part of the periodic table of elements, and it's a halogen combined with various metals. So for example, sodium combined with bromine gives us sodium bromide. Combining these two together will give us the silver bromide. That's the light sensitive material that we need, and we're going to keep that, and that's what we're going to use to make a light sensitive material. Now, what we need, since we have our light sensitive material, we also need a binder, so something that can, a vehicle to hold this light sensitive material in suspension. Okay, and in this case we're using gelatin, and gelatin is the leftover parts and pieces of animals, the connective tissue, and when it's broken down it creates a perfect material to suspend light sensitive material or sugar and food coloring to make a delicious treat. The first person to do experiments with gelatin as a photographic support was Richard Leach Maddox, an Englishman, and his experiments and inventions essentially lead to the invention of the gelatin dry plate. And here is an example of, on the left we have just a solution of water with silver and bromide, okay, and you notice that it forms a precipitate here at the bottom. So all of the, when it combines together in the water, it crashes out and lands on the bottom. With the addition of just 2% gelatin, you'll notice that the precipitate on the left that's crashed out is held in suspension. Okay, so it's evenly distributed throughout the solution, which is great. That's exactly what we needed to do. Okay, so to create this, what we have to do is add gelatin to cold water, okay, and we'll allow this to swell. Once it's swollen, we'll then add either our bromide, iodide, or both, depending on the formula, to the swollen gelatin, and we'll melt this. We will then dissolve or add silver nitrate into water. We'll dissolve that, and now we have a part A and a part B. Okay, so the silver nitrate, the part B, will be squeezed into the kettle here, which is part A, containing our gelatin and halide solution. When the ball is squeezed, the gelatin will be shot or forced into the kettle there, and the precipitation and emulsification will happen. So you notice how it's a sort of clear color now, and then after the addition, this is under white light, just so you could see for example purposes. You can see how it's changed color. It has a yellowish color to it, and it's almost very milky. You can't see through it anymore because that silver has precipitated and is in suspension throughout the entire gelatin solution. What has to happen next is we will put that solution into a fridge and let it cool. We'll then noodle it, which means we're going to break it apart into the smallest little bits and pieces that we can possibly get it broken apart into, and then we're going to wash it. So physically dunk the noodles into water to remove the nitrates. That's the byproduct of the silver nitrate and sodium bromide reaction. So we will get silver bromide, and we also get sodium nitrate, and that's what we want to remove because that's a nasty byproduct. It's not nasty, but it's a byproduct that we do not want and would contribute to fog if we were to try to coat that onto plates. It's then drained and the noodles are washed, and then we let them dry. We scoop it out and then we remelt it, and then we'll add what's called phenyls. So an example of a phenyl would be something like thymol, which is an active ingredient in mouthwash, and it's like Listerine, and it's a anti-fungicide, so it'll help prevent bacteria from growing within the solution here. Okay, so now the easiest thing to do is to coat these photographic plates, so pieces of glass, and we would coat them by hand. You would take a piece of glass, and here this fella has a gravy separator or some sort of vessel or beaker to pour your emulsion onto a plate. It's poured, spread across the entire area of the plate and then placed on a cool level surface, and will allow it to set up as a firm jelly and then eventually dry into a hard gelatin layer. Now, if we were going to make these by hand, one at a time, maybe make a few in my darkroom, that's easy. But if we were trying to make this as an industry or a business, we need apparatus to coat these things. So you can see here, this is an early Eastman plate coating apparatus. Suction cups at H will hold G, the glass plate, pass it over A, which is a roller, which will dip down into B, which contains hot emulsion, and leaving a fine layer of thin gelatin emulsion across the top of the plate. So this would make it easier to make mass amounts quickly instead of having, lots of people stand there and coat by hand. Now these plates are only sensitive to ultraviolet, violet, and blue light. So mostly sensitive to violet and blue light, but plain emulsion. These plain emulsions, as you can see here, as this showing the visible spectrum, so ordinary film, these are the colors that these emulsions are only sensitive to. So panchromatic is something like our digital cameras, or if you were to shot Tri-X or any modern black and white film, will be panchromatic. But you can see these plates or ordinary film is only sensitive to this narrow high energy wavelength light. So here's an example. This is a color image shot on Kodak gold color film, and here's an example of how that plate would render the tonality. Okay, and if you look at the cloth in the background and notice the fruits, so the cloth is blue, it gets very light, or a white tone, and the oranges, yellows, and reds, the opposite side of that spectrum, get very, very dark. So one more time, the blues, and notice the oranges, notice the vase here, watch all the changes happen. Okay, and now with these plain emulsions and with lots of apparatus for making other things, here is an early Eastman paper coating machine, and this machine would coat the paper, would bring it up onto this rack, and this festooning here means I can coat long lengths of material and store it in small areas of space. And this machine, and the idea of coating emulsions now on a flexible support, okay, the paper being the first sort of flexible supports that they're using, leads to the Kodak camera. Okay, and this was a hardened gelatin layer on top of a soft gelatin layer, which was all coated on paper support. This leads to the people starting to think about moving pictures. Okay, but the thing is, we can't coat, you can't really make moving pictures on paper support easily. So the thoughts, people start to begin to think about transparent, flexible film support. And the person who really makes the largest influence on this is George Eastman. And here's some examples of Mr. Eastman's notebook with early samples and tests of early nitrate film support. And that's ultimately what they end up with. They start, people start thinking about making moving pictures or multiple pictures on paper with the flexible support, but a clear, transparent base is what's needed. And thus we have nitrate film, or nitrocellulose solution. So nitrated cellulose or cotton dissolved in ether and alcohol. So here we have nitrated cotton, so cotton that would have been soaked in nitric acid, dissolved into equal parts of ether and alcohol. We shake it up and it's completely dissolved, and we're left behind with a clear liquid that can be coated. It will dry, and then we can put that gelatin emulsion layer right on top of that. And this was made with the casting and coating tables. Okay, and what would happen was, here, this hopper, this is an example of the first ways that long lengths of flexible, transparent film support were made. And what would happen is this hopper would be brought all the way down to this side of the table and loaded with hot nitrocellulose solution. This would be cast, and they would crank this all the way down to the other side of the table. They would open up the windows, allow everything to evaporate off, and once it was dried, probably at night, they would turn on the safe lights, close the windows again, crank the hopper back down to the other side of the table. Now they would fill it with hot liquid gelatin emulsion, crank that all the way down and would lay down a very fine ribbon of emulsion on top of this glass table. Once that's dried, they would go ahead and they would slit these lengths of film all the way from one side of the table to the other, and that would be one length of film. Okay, and this leads to the improved Kodak camera, which was on a nitrocellulose or flexible transparent film support. The original Kodak was on the paper support, and it worked, but it wasn't the best material to be using, and they did soon realize that the flexible transparent support was the way to go. Now, this attracts the likes of people like Thomas Edison or W.H.L. Dixon, who saw the potential in this material to be used for the things that they were interested in, and going ahead and moving and start to making moving images and motion picture films. Here is late George Eastman and Edison in the gardens at the George Eastman Museum. It's quite a treat to look at this picture and then go back to the very same spot where these two captains of industry were testing material, and to go ahead and test our own handmade material right there in the same sort of spot. It's very exciting for us and the students who come to the workshop. So the use of flexible transparent material is what helps to enable the motion picture industry to begin to grow and turn into what we have now today. Now, here's how we keep this technology, this early technology, alive with the help of some modern pieces. So here we have an X-Polaroid film coating machine that was X-Polaroid. It went to RIT, and then my boss Mark Osterman eventually inherited this, and it sat in his basement for 10 years until I showed up. We cleaned it up, put it back together, and now there's no instructions on how to do this. So there was a lot of empirical testing going on, because you have your slits, your speeds, and so many little variables that all have to align at once that make it quite a challenge, but when you get it right, it's fantastic. So first, a flexible support. In this case, we're using polyester. We also have acetate film-based support, so 5 inches wide by 6 inches long, or 6 feet long. Then once the film base is on and it's tensioned, we go ahead and we put on the coating head. And you can see here this plastic shim dictates the space between the top and the bottom, which allows for the slit for the gelatin emulsion to pass out of the head and onto the flexible support. This tube is attached to the top of the head, which will feed the hot gelatin out of an intrusion pump at a consistent rate into the top of the coating blade here, which will then distribute out onto the film support. Here's the film coating machine running now, so we would turn on the pump. Once we can see a gelatin bead form across here, we flip the switch and the emulsion will be taken away across on the flexible support. We let it run, and eventually we get a whole length of film that's coated, and we'll stop the machine, withdraw the head, and then carefully remove the flexible support from the machine. Once it's dried completely, we use a splicer, a 35mm splicer, which will take that 5-inch length of film and knock it down into 3 35mm lengths of film. Now this is the only way that we can still do this stuff at the museum, okay, is because we have this 35mm perforator. This was a Bell & Howell perforator, and this would have been doing 120 feet per second in the dark up at Kodak Park. They decided they no longer needed that, and they bequeathed it to us. And because of this piece of apparatus, we're able to perforate 35mm film stock that we can shoot in any 35mm camera. And here is an example of it after the perforations are placed in there. We'll then take this film, splice a leader on the front or back, and then we can load that into a 35mm camera. We use an old IMO camera, and we're able to shoot videos or films right out in our garden. And it's a fantastic treat. If you ever have a chance to make it out to Rochester, New York, I encourage you to come and see some of the things that we're doing, and I hope that you enjoyed this short presentation. Thank you very much. Have a nice day.